right. What? Oh, you want me to use the mic? Okay, here we go. Can you hear me? All right. Hi, everybody. Thanks for coming. It is my great pleasure to introduce my former PhD advisor, Susan Beck, for our colloquium speaker today. Susan's at the University of Arizona. She started off more in geology and in structural geology. She got her undergraduate and master's degree at Utah in that, and then came to the dark side of geophysics and switched, went to the University of Michigan, got her PhD in seismology with Larry Ruff and Thorne Lay, and then did an internship at Lawrence Livermore, and then ended up at the University of Arizona. Susan she's sort of one of the early pioneers using the Pascal Instrument Center, so using portable seismometers to go out to areas of interest, study the tectonics in the region, collect the data, do all the analyses, and figure out what's going on. And so she really led the way on that. And I think today she'll be telling us a lot about sort of a look over all of that we've learned, especially in South America, where she's done a ton of work on all of that research there. So I think with that, I will just turn it over.
Well, thank you, Laura. Can everybody hear me? I'm pleased to be here. It's always fun to talk about your work, and it's always fun to work with Laura because she keeps me honest and keeps me on track, which sometimes I need a little push. But what I want to talk about today is again, some overviews, touch on about 4 different topics of work we've been doing in South America. And a lot of this work I'll be showing is some of my current graduate students, which are listed on the top, and a few things brought in from former PhD students, but things our group at the University of Arizona has been working on. And as you know, I work a lot in South America in the subduction zone and the Andes. I didn't start out thinking that was going to be my primary focus, but things just kept going. And it's a great subduction zone to look at in mountain range. It has a lot of analogs around the world, but it's a big, long mountain belt. It's a Cordilleran-style mountain belt, and so there's a lot of analogs with the western US during the Mesozoic tectonic history. It also has magnitude 8 earthquakes, about 1 every 10 years. And although I'm not going to talk about that, that's a focus of some more recent work we're doing now to try to look at that. As most of you know, as you look along strike, there's noticeable gaps in the arc volcanoes. Here's the red triangles of the arc volcanoes. There's gaps down here in Argentina and Chile where the Juan Fernandez Ridge is coming in. And also up here in Peru, a much larger flat slab. The southern end of it correlates with the Nazca Ridge subduction. There are deep earthquakes, particularly in the center part of the subducting Nazca plate. These are earthquakes as a function of depth, but the deep earthquakes sort of end about here. To the south, you don't see them. To the north, you don't see them. And of course, I'm not showing it, but the age of the downgoing plate in the center is 45, maybe close to 50 million years, and it decreases north and south. But in general, this whole range between the 2 flat slabs, the age doesn't change a whole lot. So that's one thing that's nice. The more variables we can keep constant, the easier it is to look at things. And of course, there's a lot of shortening and some big ignimbrite flare-ups. So you can kind of work on whatever you want in South America. The key, of course, if you're a seismologist, is where do you get data? So I've divided the talk into sort of 4 areas where I want to talk about some of the things that we've been thinking about. And one is mapping out just in detail the geometry of the slab and how it deforms and what happens in the mantle transition zone in the lower mantle. We have global models that give us some pretty good clues, but in terms of a more detailed model. And then, of course, the age-old problem of looking at crustal thickness and lithospheric structure and how that relates to topography, we've made a little progress in. And we've done a lot in looking at large-scale plumbing systems in magma regions with large ignimbrite flare-ups. And then finally, I'll just touch a little bit on flat slabs if I have time. But I'm sure you've heard Laura talk about that, and she's perhaps more of an expert than I am. So where do we get data? Well, for me, this This started in 1992 when I made my first trip to South America and began making contacts, and I did my first seismic broadband deployment in 1994. We were so pleased with ourselves. We had 20 stations. You know, that was a huge deal. And, you know, we'd go down and do the usual thing, put up, get sensors and bury them and put up solar panels. And someone can tell you that this terrain is not so easy to work in. But these stations, plotted all with the same symbol, look great. Oh, yeah, we've covered a lot of South America. Our group has done about 400, been involved in deploying about 400 of these. And this has about almost 1,100 stations on it. So certainly, I don't want to take credit for this, but a lot of people have worked a lot in this region. The Germans have done a lot of deployments, the Brazilians. And I'll show you a later figure where I've broken it up into different groups. But it's really been putting all that data together, much of it open data, that's allowed us to do what we're doing. And we collaborate with a lot of the Latin Americans on this. But we're starting to get a good picture of station coverage, but you can see some major gaps. Northern Peru is a major gap. So at shallow levels, we can't image much. Brazil is not uniform. Of course, the Andes are much tighter station spacings. So I'll talk about how that impacts our results. So I first want to just jump in and talk about part one, and that is imaging the Nazca slab. These are images of the transition zone, and then going the top two, and then the bottom two are images deeper than that. So this is P-wave finite frequency tomography, where you look at different frequency bands. For the P waves, I'm not sure that gives us a whole lot. It helps a little bit. For S waves, it makes more of a difference, but we're trying to process things the same way. So this is work by Daniel Portner, one of my PhD students. This is his work, ongoing work, but we're pretty close to a final model here. And so we make crustal thickness corrections. You can imagine the variations in crustal thickness here make a difference, and a little bit in crustal velocity. But we have variable node spacing. So this is an image where in the Andes, we have node spacings that start at 35 kilometers and expand with depth. In Brazil, our node spacing starts at 85 and expands with depth. So we have to be a little bit careful. We're not going to see the same detail. But we do that because of the station spacing. We've tried uniform grids and all that as well. So we'll be, of course, getting into all those details. But even at 410 kilometers depth, and of course, blue is fast, red is slow. This is perturbations in velocity because it's teleseismic tomography, so it's plus or minus 5%. But that's pretty good. Most global models are maybe plus or minus 1% or 1.5. And you see the slab at 410 pretty nicely, except for this gap up here. And that's lack of data. That's not a gap in the slab. However, this is probably a real gap. And then down here, again, we kind of lose it. But as we go deeper, we're getting crossing rays. And so we can really begin to see the entire slab all the way up into Ecuador and Colombia on the Pacific side. And then as we go deeper, we see that it all penetrates, the slab penetrates through. And as we go even deeper, we sort of lose the slab in here. Maybe it's off here, but for sure we can see this big blue area that we're interpreting as the slab sort of piling up below the transition zone. We've also done the equivalent thing with S waves. And I'm just going to show you a couple of cross sections with the S waves. We have a little bit less data, but we've still got over 1,000 stations. And we're using S waves at SKS phases. So for those of you in seismology, the S waves are SH, the SKS are SV. So we have made a correction because we have shear wave splitting at most of these stations. So we've corrected the SKS if there's splitting at that station. We don't know where that splitting is. It's an average. We've compared before and after, and I'd love to talk to people about whether that's a good correction. But what I'm showing includes that correction. And again, we're using the variable node spacing and made crustal thickness corrections. I'm just going to show you 3 cross sections to show you some of the variation here. So here's our 3 cross sections going from north to south. And once again, we've been seeing this near vertical slab in Peru at the south edge of the flat slab. So here are the earthquakes in green, the slab is flat, and then it goes down. Now, of course, we don't image things above about 150 kilometers very well for a variety of reasons that we could get into later. But we really see the slab coming down and spreading out. Our images go deeper than 1200, but we get edge effects. So this is about where we were comfortable interpreting it. In the central Andes, here's our slab coming down. The earthquakes match it quite nicely. Still some pile up below the transition zone. And then further south, we see the slab, but it's not quite as strong an amplitude. And that is an artifact. We just don't recover the true amplitude very well. But what I want to draw your attention to is perhaps we're seeing the edge of one of the cratons here. If so, it seems like it has a pretty deep depth extent, but a little bit of this might be smearing. And then below the slab are these blue anomalies that keep showing up. And people are starting to say, well, maybe those are slab fragments. And we've been looking at the tectonic history. It's a little bit hard to figure out how a piece of slab would break off and be there below the slab and not in front of the slab. But nonetheless, it's interesting to think about what that might be. It might be something totally different. Yeah. They fit nicely. I didn't happen to pick any, but like there's one just near here, the deep focus earthquakes fall right on the slab. I've got some images on my computer I could show you later. But no, the earthquakes are right in the slab. We've just projected earthquakes, I think 50 kilometers or so on either side of this, or maybe 40 if I'm not mistaken. But yeah, where there are deep earthquakes, they fit the slabs beautifully. I should have put one of those in. So one of the things that I think has caught my attention is how do you go from a flat slab to this near vertical slab and bend it? And there's not a lot of earthquakes that look like bending earthquakes in that part of the slab. In fact, the Peru flat slab doesn't have all that many earthquakes compared to the Argentine flat slab. So to me, it suggests something pretty interesting about the rheology of the slab, that it must be weak enough to bend without producing bending earthquakes. The other thing that we see in all these images is a lot of low velocities back here. In this cross section, it looks like it goes all the way down. In other places, it looks more isolated in the upper 400 kilometers, but in both P and S waves. So there does seem to be some low velocity below the slab, and I'll show you a little bit more about that if I have time. So we're seeing a lot of different things in these images that we really think we have much better resolution on. We're doing a lot of bootstrapping to look at errors. With this much data, we can begin to really map out where things are well resolved and where they aren't. I want to now move to a shallower part, sort of get into part 2 of the talk, and that is, what do we know about the upper mantle? There's a lot of interest, and I'm particularly interested in the mantle wedge. It's a complicated region, and it's sort of, between our teleseismic tomography models and our crustal kinds of models, and using ambient noise and surface waves is a good way to look at this. And this is work by Kevin Ward that came out 2016 that we've continued to work on. But this is a blow up now of this is Lake Titicaca, so Peru and Bolivia are right here. And this is a region we did a deployment. Laura was involved in this work. And by combining the ambient noise, which gives you higher frequencies, and the earthquake-generated surface waves, we can get down to about 150 to 200 kilometers with pretty good resolution. So here are two cross sections, B and D, shown right here. Here's our subducting slab in blue. The crustal velocities are one scale, absolute velocities, and the mantle velocities are a different scale. It's probably hard to read that, but those are perturbations. And the thing I want to highlight is, one, we had good crustal thickness estimates, so that provided a good constraint. But what we see are these really regions of low S-wave velocity isolated above the slab that, again, suggest things might be hydrated. Of course, we always want more information. And then we consistently see some high velocities localized right here. So that gets us into thinking about lithospheric removal and those kinds of problems. But this is right under Lake Titicaca, which is a big hole, and a lot of times we always wonder, well, why is there a lake there? It's a pretty deep lake, in fact. And again, it looks like it may be coming from some extra density below the crust. There's also now some xenolith studies done where this red yellow star is, coming from about 60 kilometers depth. And although it's always a little bit tricky to compare, these are very young xenoliths, and they have some mantle material that Chapman and others, Alan Chapman was a postdoc in our department, interpreting as a phenosphere. So we're seeing some high velocity material. They're sampling sort of right between it. And we're still kind of working on that. The question I always have, are xenoliths a good representation of what's down there? Because as our images get better, we'd sure like to be able to put those things together and see what they tell us. In map view, you can see this again a little bit better. Here's the high velocity material at 80 kilometers depth. Here's that really low velocity hydrated material. This is right where the slab changes dip. And again, at 100 kilometers, you can still see it. The anomaly for the high velocity material is a little bit weaker. And here's the slab for reference out here. So we think we're seeing the remnants. Our interpretation is that we're seeing the remnants of some of the lithospheric material that's probably in the process of being removed. There's not much left, but there's a little bit. If we want to look at the whole mantle wedge at this scale, from Peru down into Argentina, we have to sort of piecemeal it right now. We're trying to put all this together in one inversion. But the blue areas come from different studies, but they're high velocity material, whether it's S or P waves. And the reds are slow velocities at this depth range of 80 to 90 kilometers. And again, we'd like to have all P or all S, but this is what we have from localized studies, and you can see the names associated with them. But most of this work is from the University of Arizona. If we look at that, there's this break right here where you mostly have low velocity and you mostly have some high velocity material, which is not all that unexpected when you look at a cross section going from south, the Puna Plateau, to the Altiplano. And this is elevation. Looks like my labels got cut off. So the Puna is on average at least a kilometer higher. And of course, this is where we don't see much mantle continental lithosphere left, whereas up in the Altiplano, we do. And if you know anything about the Puna, the first thing you think about is volcanics. There's huge ignimbrite flare-ups, magmatic flare-ups in the back arc, some of the biggest ones on Earth. These things are bigger than Yellowstone. They rival the San Juans in Colorado. So it's a major, major ignimbrite flare-up that a lot of geochemists have worked on over the years. But to first order, this really fits. And I think we knew this from years ago, but we didn't really have the data to show it. We just thought with all that volcanic activity, there can't be that much mantle lithosphere left. But it's nice to be able to confirm it. And as far as crustal thickness goes, a lot of work goes into this, and we conclude, well, high elevations have thick crust. In the Altiplano, it's 65 to 75 kilometers thick, and as you go east, it thins. But there are areas that I'm pretty convinced are a little bit over-thickened and a little bit thinner. And I've just, in blue, plotted on the scale of the central Andes. This area in Peru has a little bit thinner crust. There's a little bit thinner crust here in the Puna. And then we've got areas that are sort of over-thickened. And of course, the tendency today is to compare that to overall crustal shortening in the thrust belts. And this is a plot of shortening in kilometers from north to south. And in the central Andes, where we have the thickest crust, we have 300 to 400 kilometers of shortening, depending on which study you look at. So a lot of shortening. And then it dies off to the north and the south. And I think that's been known for a long time. But question is why? And we could be missing some shortening. But one of the things we've consistently noticed is the crust is really thick here. Here is 75 to 65 to 70. And yet the shortening amounts are thought to be pretty low. Now, maybe, again, some shortening has been missed. So that's led to speculation that, OK, we get thick crust here, and it flows, crustal flow. That's a big topic in Tibet, how the mid-crust is flowing. And of course, it seems reasonable that it might happen here, but how do you show that, And so one of the ways we wanted to do it was to look for radial anisotropy. Can we see some layering or some kind of fabric in the crust as a whole? And if you've ever done this, it's a little tricky. And like a lot of things with anisotropy, it's non-unique. But we've done Rayleigh wave and Love wave tomography to get velocity models. And of course, Love waves are SH and Rayleigh waves are SV. And at this point, there's not a really good way to invert them together. But if you just look at the differences, you see some interesting patterns on a crustal scale. And the idea would be is if there's either magma storage or some kind of layered structure or mineral alignments or something, you might see this kind of fabric. And indeed, that's what we see. This is a cross-section from B to B prime going along the length of the altiplano through and into the Puna in the thick crust. This is work by Colton Linner, who just finished up a postdoc with me. And so it goes through the altiplano and then into the Puna. And what we see, which I think is well resolved, is that at least down to 40 kilometers or so, we have good resolution, that this part shows anisotropy, horizontal layering, and the blues indicate that there isn't any. And so there is this region in the mid-crust that seems like it's at least possible that it could flow. Now, we don't know if it is. Could be something frozen in, but the crust is still thick. And so it's likely that it could be showing us that there's some mid-crustal flow. Now, the question is, which way is it flowing? And of course, the people that work on this are excited because, oh, now it could be flowing from the central part to the northern part where we see thick crust with less shortening. So that's certainly a possibility that it's flowing from this thick part into this part. As we come down here into the Puna, this is the Altiplano Puna Volcanic Complex, one of these big magma flare-ups. And this would be the area between 15 and 25 kilometers where there's really high low velocities. So probably that anisotropy may be this idea of horizontal layering in the magma chamber at that depth. So whenever you see this, there can be multiple ways to interpret it. And what we can really see is that there's some fabric there that's giving us clues to what might be going on. So in the end, for the central Andes, we're starting to get a pretty good picture of a lot of these ideas, the subducting slab, the earthquakes, areas that may be hydrated in serpentine up here in the wedge, partial melt zones coming off the slab, a little bit of high velocity materials, probably eclogite now, and then going off to the east. One thing we don't really see very well is the edge of the craton. So we need a little more data for that. Now I want to talk a little bit about, and please stop and ask me questions if you want. I'm trying to give you a little bit of a highlight of different things. I want to go to the imaging the magma processes. And we do pretty large scale imaging, as you can see. So we weren't really sure what we would see. But a number of years ago, we got very interested in southern Bolivia. Actually started in 1997 was our first Arizona deployment there. Because this was an area everyone talked about being one of the biggest ignimbrite fields on Earth. And the APVC, it's a big volcanic ignimbrite field. It's about, the majority of the ages are 1 to 11 million years, so it's fairly young, probably still active. But there's a lot of volcanic activity down here. The red are the sort of the big stratovolcanoes, but there's another back arc caldera called Cerro Galán that's worked on by a lot of people, particularly Sue Kay. And so we thought, well, if we're ever going to see something in the crust, this would be a good place to look. So after a series of deployments by us and other people, there's plenty of coverage down there now. And what we were going after were things like this, although this is a recent diagram from De Silva and Kay, and I would say that they used a lot of our work to draw these kinds of cartoons. But these kinds of things were around before that, where there's some kind of maybe mash zone near the moho, which we would see as a gradational moho. And then there's some kind of upper crustal, fairly large region that's, again, a mash zone. It's been called the Altiplano Puna magma body, but we know it's not just pure magma. And so this would be another place where it pools and then eventually makes it up to the surface to erupt. But this is, in the case of the APVC, it's a huge, huge area. And so we've been working on it for some time. And I think it's some of the best images I've ever seen for this kind of thing at this scale. So now here's a blow-up of the region of the Puna. And the surface outline of the APVC is this dark rust-colored area. So it's pretty big, right where Bolivia, Argentina, and Chile come together. And then there's plenty of other calderas you can see in this topography. Here's Cerro Galán right here. And so these have been sites where people are suggesting that batholiths are forming today. A lot of people compare this to the Sierra Nevada batholith and the Canadian Cordillera batholith and stuff. And this question of how batholiths form, and are there big batholiths under every arc, or do you need special magmatic flare-up conditions? And I can't answer those questions, but we can look at this and then compare it to others around the world and see what this is telling us. So in here, there's one volcano, Urunku, that's had, based on GPS and INSAR, been inflating. And so it seemed like a good target, and that's what got us going. Even before some of these papers came out, there was talk of this. And then Cerro Galán is an active, large silicic volcanic field and caldera with sort of less than 3 million years old. So it's very active. And we know there's very little mantle lithosphere beneath these regions. So we thought, well, what does the crust look like? And we'd go in and try to look at these with several kinds of imaging. So the first thing that Kevin Ward and Jonathan Delft did to former PhD students is, of course, receiver functions and ambient noise, and combine those two into a joint inversion. So the receiver functions give us discontinuities, and the ambient noise gives us sort of average velocities, so we can constrain things a little better. And you have to weight it. These are weighted at about 70% receiver functions, 30% ambient noise. But the structures are similar, however you decide to weight it. So the first cross-section is through the APVC, and the second one is down here through Cerro Galán. And the velocities go from, these are absolute crustal velocities for VS, 1.9 to 4.3. And the first thing you see up here is this big white, like less than 1.9. It's a super, super low velocity area. And Urunku is right there, one little blip. It doesn't even show up on the topography. And look how big this is. It's covering from the arc all the way into the back arc. And it's at a depth between, we get it, 18 to 25 kilometers or so. As we go further south, Cerro Galán is much more isolated. It's still a low velocity zone with S waves, but not as low. And this red is an estimate of MOHO, but what we really see, things are pretty gradational in the receiver functions. So this label, unfortunately, is I put it right on another low velocity. This is under the arc. But we can see sort of a difference between the cross-section up here through this well-developed system and perhaps one that's a little younger and just starting out here. And this has gotten quite a bit of attention, this altiplano magma body. This is sort of a three-dimension image of it. Here's Urunku, and it's just sitting right there, that one little peak. And so basically we challenged Kevin, okay, with these velocities, how much of it has some melt in it? So you have to make a decision. What we came up with was anything at that depth that has a velocity of less than 2.9 kilometers per second probably has to have some melt in it. There's just no other way to really get those velocities. And so anything white is well below that. But we thought we were being pretty conservative. And so we sort of used that as that's an assumption, but we calculated the volume of that 200 kilometer by about 11 kilometer thick body that had to have some partial melt. And when you do that, you get 500,000 cubic kilometers. So to me, that sounded big. And I thought, well, how big is that? And of course, we went to other areas and looked, and it is big. It's the biggest one that we can find. And in fact, if you start looking at some of the outcrops in Colorado and the work done in the Sierra Nevadas, they're starting to see these kinds of volumes. And of course, it correlates with all the stuff at the surface, but over a much, much bigger area. So to us, that was pretty amazing that there could be such a large area that had such low velocities. And we started thinking about, okay, how can we use this? That's great, we've identified this. But if we take cross sections from north to south again, we see sort of a progression. And we thought, well, maybe we can look at this, here's our spatial distance, but also we could think about maybe it's time. We can think of today, we've got this big magma body here. How did that form? And we thought, well, maybe at the end of flat subduction, if you buy that as being the reason the slab steepens and you get a phenosphere in that would start all this, here's one of the low velocity zones under the arc, and then it slowly, as you go north, presumably the slab has been away longer, it starts to spread out, and then it shifts over here to Cerro Galán, and then shifts back, and then eventually it all merges. And so maybe we can think of this as sort of a progression of how these things might form. They sat out as small bodies and eventually merge together through time. And the other thing we wanted to do was to try to, again, look at these plutonic to volcanic ratios. Because I sort of grew up hearing from people, oh, it's 5 to 1, it's 4 to 1. But when you take any of these and do our calculation, we're getting pretty big numbers. For the entire Puna, Kevin calculated 34 to 1. So that's the plutonic volume versus the surface erupted ignimbrites. And of course, there's a lot of error in both of these. The surface, you get the area, and then you have to get the average thickness. But we've taken that from a lot of the literature. And we got a ton of pushback on that from people initially when we tried to get it published, that just can't be right. And now, even those people that push back really, really hard on a student paper that was pretty frustrating for George and I, are now coming around and quoting this number in their 2018 papers. And I think that's in part because some of the geologists started looking at this more carefully in the San Juans, in the Sierras, in some of these other places, and said, hey, wait a minute, yeah. Now, you always have the preservation problem, right, in the geologic record, how much of the ignimbrites are still there. But down here, the Puna is really dry. It doesn't have much erosion, if you've ever been there. So we're not talking a place where there's going to be a huge amount of erosion in the last 10 million years. So that's sort of satisfying, but also a little irritating. So we estimated that this probably can't be more than 20%, and we can come up with numbers sort of whatever you want, from 8 to 20%. An MT study over this same region, looking at resistivity and stuff, they came up, and petrology, they came up with 15% partial melt. They see the top of this body, a few kilometers different than we do, but not much, a couple kilometers shallower, their best guess, but it's the same feature. And then, of course, MT can't see the bottom of it. But totally independently, they came up with this 15%. So again, that's huge, at least to me, because I'm thinking, even a few percent partial melt can slow down seismic velocities. So we're continuing to look at this, but as far as I can tell, at least in the Andes, this is by far the largest. We see small features associated with the arc, but nothing of this scale. So you can take it a step further and say, well, what about, okay, what led to all of this? And that gets into the volcanic record, and I'm certainly not a volcanologist or petrologist. But our best guess is that the flat slab, if you look at the slab reconstructions, this is the slab the ridge has a kink in it. So at 10 million years, this was where the Juan Fernandez Ridge was going through. And if you make the assumption that that ridge is a big part of why there's flat subduction, that's where it would be at 14 million years through here and at 18 million years here. And you can shift these a little bit based on the reconstructions. And the further back in time you go, probably the bigger error. But, and then you can take regions of age versus longitude and plot all the, from a database that Trumbull has put together in 2006, includes everything. So the arc plus the back arc, I think blue are ignimbrites, and red and yellows are arc, and based on petrology a little bit. But at the scale I'm looking at it, I'm just looking at patterns. And so what I see is, a change at about 30 to 35. You got the arc going on. Maybe we missed a lot of back arc volcanism at that age. Of course, you don't know how complete these databases are. But everything seems to be going along. And then things go to hell, sort of, where you get all this back arc stuff at 30 to 35 million years. And then somewhere, and maybe a little bit of an arc lull. But it doesn't quite fit with the timing of the flat slab going through. Here's the blue is where the Juan Fernandez Ridge passed through. And again, I'm saying that's a proxy for flat slab. Maybe that's right, maybe not. But certainly what I expected to see was a pattern when this projected flat slab went through. Then we'd see all the back arc volcanism. You remove the slab, you're going to get all the flare-ups. And yet it seems like it starts well before that. And I don't have an answer to this exactly, except that I think we're seeing two different processes. One may be the slab coming through, but also lithospheric removal seems to be a big process in the Andes. We don't see a lot of high velocity lower crust in many places, and it looks like any continental mantle material has likely been removed. And at least in the central Andes, we don't have a lot of old terrains. It's mostly built on the South American margin. So I think we've got these competing processes that are probably making it a little more difficult to say that this magmatic flare-up is due to one or the other. But a lot of what we're looking at, here's the age of the APVC. It is right after this ridge passes through. Cerro Galán is right here in terms of location and age. So I think we need a little bit better databases and more information about some of the ages of these arc rocks. But these patterns, of course, are more complicated than we thought. And we need to keep both of those in mind in terms of what are driving these magmatic arc flare-ups. And finally, with just a few minutes left, I want to focus on the flat slab in the last part of the talk. And I'm just going to show you a few highlights of things that I've been looking at recently. This is the Argentina-Chile flat slab. Here's a Juan Fernandez Ridge. It's not that big a thing. It's a series of seamounts coming in. So it's nothing like the Nazca Ridge. Offshore, the oceanic crust has been imaged from being normal to being maybe 13 kilometers thick, not overly thick. But here are the earthquakes just from the PDE catalog, magnitude 4 and larger, I believe, below about 50 kilometers or so. Well, it includes some 50 kilometers, I better not say. We tried to leave off some of the trench ones. But anyway, you can see all this seismicity and slab contours that we maybe revised. Maybe that's a little tight. But at any rate, you can see where the ridge comes in. There's a lot of earthquakes. And any database you look at is there. It looks like that. And we see crustal earthquakes that are pretty deep, too. And I'll get to that in a minute. So here's some of the seismic stations we've used for some of the imaging. The ridge is coming in. Relocated earthquakes using double difference for a period of 2 years show the earthquakes are indeed pretty flat, right? This line is 100 kilometers, so we think that's the slab going down. One question is, are those earthquakes in the downgoing crust or the mantle part of the slab? And that becomes important. And I'll just tell you, my thinking has evolved on that. And I think maybe that they're in the, actually the mantle part of the slab, not the crust. But one of the really interesting things is looking at receiver functions. So this is where you use P to S conversions to map out discontinuities. It doesn't tell you about velocity, but as you go down in depth, an increase in velocity is red and a decrease in velocity is blue. And if you stack all these things, we can begin to see things like the continental moho in red. It decreases in amplitude, but you can see it pretty well as this red. But what really stands out on these images, and granted they're saturated a little bit, work by Christine Gans, is this blue and red. And we interpret that to be the top of the slow oceanic crust and the oceanic moho in red. So there's the top of the oceanic crust, there's the bottom. This was migrated with a particular velocity structure, so there's a trade-off there. But we think we're seeing the oceanic crust, and then bam, it stops. And the slab continues on. And so we've taken that to be sort of the edge of where this basaltic oceanic crust is transformed to eclogite, and now it just looks like mantle. So that's one thing that in many of these flat slab regions, or even dipping slab regions, we can map where that boundary is. And I think that's an important boundary that I want to focus on just a little bit. So with surface wave tomography, we can see the flat slab pretty nicely sticking out here. This is an image of velocity perturbations at a depth slice between 110 and 120 kilometers. So we see that pretty nicely. If we look in more detail across section through here now where we've plotted absolute velocities in the crust and the mantle, this is work by Ryan Porter, who's now a faculty member at the University of Northern Arizona. We see the slab going down, but the slab doesn't look as high velocity as we thought. It looks like it might be pretty hydrated with some of these lower S-wave velocities. We see the corner flow maybe starting up again here as it dips down, maybe the edge of the craton. And then we see some lower S velocities here. Laura's done a lot of work on this, so I'm not going to get into it too much. But Ryan's idea was as the slab is bending, the earthquakes are there, they're releasing water, but it can't get up into the overriding plate. But as it comes down here and starts to bend, maybe you can get the fluids out. And so they're not just all going up uniformly, but they have pathways. And with more recent local tomography, we're starting to see that pattern, which I don't have time to show you today, but it seems like it's not so simple as we've known for some time. But what I really want to get to is something that I'm pretty excited about that Daniel Portner has imaged, and that's a tear in the slab associated with the flat slab. So again, here's all the seismic stations Daniel used in this inversion, and here they're color-coded by different deployment. And the reason that's important is to give credit. I can't give credit to every single person associated with this, but it's many tens and tens of people. And now, as I said, as we put all this data together, it begins to make a lot more sense. So there's a lot of people that have been involved in this data collection over the last 20 years. So again, using P-wave tomography and lots of earthquakes and both direct P-wave and core phases, Daniel's been able to come up with some pretty good images. So in map view at a depth of 320 kilometers, here's the slab going down, here's the slab down here, and there's this gap in the slab where there's lower velocities. And this shows up no matter how you do the tomography at this depth range. And in cross section, here's our flat slab coming down, here's a gap, here's the deeper part of the slab. So it seems to go from about 200, 250 kilometers down to 410 in there. It's a pretty big gap. John Booker has seen MT images of something that looks like it has fluids or has coming through here and interprets it as sort of a plume coming up and breaking through the slab. We're not so sure. We've been thinking more about entrained asthenosphere because the Juan Fernandez Ridge formed as a hotspot. There may be some warm asthenosphere under there, and it seems not so hard to get entrainment as the slab goes down, and then it happens to find this gap. We're less sure geodynamically that you could have a plume kind of burn through it, but rather you might have created the gap in the slab just because the flat slab is pretty strongly coupled, the deep slab is still pulling down, you're going to make the tear, and then wherever the material, the slow velocity material comes from, it can flow through that gap. So that was a great idea, and we did a lot of tests. This was an input. This was the output from our recovery tests in the tomography. I think I'll skip that because I'm a little behind. But basically trying to convince people that it was really recoverable with our data set. So one of the things that we went back to all the SKS splitting that we had done and others had done and said, well, okay, is there any chance that we could see this in the splitting measurements? Because we always were unsure how to interpret the splitting measurements around the flat slab. They changed, and we had been sitting on some data for quite a while, not really able to come up with the punchline. And so when we got this tomography, it became clear. Colton Linner jumped on it with Daniel Portner. So here are stations in the region where there's good shear wave splitting measurements. These are all data we've collected and had made measurements that we've been sitting on. And all the measurements through here, as I'll show you, are east-west. They're north-south down here. So if we just look at that, shear wave splitting is always a bit messy. But down here, they're pretty nicely north-south, parallel to the strike of the slab. Here, they really turn east-west and over a fairly short distance. And then up here, it's a mess. And these are not measurements that we made, but you can see in the Rose diagrams, they're just all over the place. But it struck us that there was a pretty good change in coherency. And so our interpretation is that the entrained material is flowing through that, and it's imparting a pretty good signal to the shear wave splitting. It's not that there isn't some component that's shallower, in the upper part, but it's really dominating. And so perhaps we're seeing that coupled with the MT, coupled with the tomography. We're convinced that there really is this tear, a gap in the slab that corresponds with the location of the flat slab. So here's another diagram where you might form the plume. It gets entrained and it comes on through. And it's down dip of the flat slab. It's not right at the flat slab. There's been modeling that puts tears right in the horizontal part of the slab, and we just don't see that. And of course, there's modeling that suggests with the age of the plate, the Nazca plate, and the velocities, that there could be significant entrainment given those particular viscosities and stuff. Yeah. Well, John Booker has a paper, and we've talked to him. He's thinking that there might be a plume that's sourced in the transition zone that's coming up. And of course, we see low velocities there too. We can't completely rule it out. But with his deep MT work, he thinks it's more likely coming from the transition zone. We have a hard time just thinking about why you would form something in the transition zone that would rise. Seems easier to be pulling it down and then it goes through. But he's got a Nature paper a number of years ago where he makes the case. And of course, he doesn't have seismic images so much as he's got the MT work. And it does show things coming from, his MT anomalies are below the slab and above it. Now with MT, again, you can't see the bottom of things very well. But it's very nice work. And I think we're seeing the same thing. We might just be interpreting it slightly differently. And I'm not 100% sure he's wrong. Our newest S-wave models do show more low velocity material there in the transition zone. So it's possible, but I just can't quite wrap my mind around how you would get something sourced in the transition zone that would be rising like that. But maybe people have ideas. I'd love to hear them. I think it's still a ongoing debate as to how best to interpret that and where that low velocity material might be coming from. And we sort of picked up on this idea that there's a hot spot that formed it, and we sort of see something similar up in the Nazca Ridge where there's some low velocity material under the Peru flat slab. But in reality, now that we've gotten better images, we see low velocities below the slab in other places too. So it's not a perfect correlation. But initially, where we had the best data, we were seeing that, and that kind of got us off on thinking about entrainment. And there's papers on entrainment in the Cascadia subduction zone in Tonga, South Pacific. So again, you always get influenced by seeing some of that. But I would say it's a bit of an open question, and we're certainly trying to pursue that a little more. Okay, so this is our cartoon for the Argentina flat slab. Here's all the earthquakes in the slab. Here's earthquakes in the crust I didn't really talk about, but they're deep. Of course, there's exaggeration above sea level here in the topography, go down to 35 or 40 kilometers. So everything points to things being pretty cold here. And that's somewhat different than in Peru, where we have the big Nazca Ridge coming in. And I think I'm probably running a little over, so I won't, I'll skip a couple of slides. But this is another area, the southern end of the Peru flat slab, with a big ridge subducting. This ridge is, the offshore geophysics suggests the oceanic crust is about 18 kilometers thick, so a much bigger ridge. And again, with the receiver function stacks, we see the oceanic moho, but it ends right here. Earthquakes continue. From other studies, the slab goes down under and then resubducts here very steeply. So here we've got the conundrum that if we're right and that becomes eclogite, it should be higher density, and yet the slab stays flat for a long time. I would expect it to start resubducting sooner, but we're pretty sure it doesn't resubduct any sooner. So I think I'll skip that for a minute and just show you this. It's one of my last slides. So here is a slightly older version of the S-wave tomography at a depth of 130 kilometers. Here's the velocity perturbations, again, plus or minus 9%. There's a big red low here, and it suggests to us that perhaps this subslab anomaly is helping to hold the slab up a little bit. There's, of course, a lot more going on to this flat subduction than I can talk about. In fact, it's one of the reasons I'm here to work with Laura, is we're trying to sort all this out and put all the data together. So I'll just stop there. I hope what I've shown you in a rather brisk fashion, I know, is sort of 4 different parts of our seismic imaging of the South America subduction zone in the Andes. And each one has a lot of interesting questions. I think we've gone a long way to answer some of those questions, but if anything, we've found new questions that we can't answer. And as the data gets better, because we're hoping to find a way to get more data up here, I think the images are only going to get better and allow us to look at even more detail. So I'll stop there, and I'm glad to take questions. Yeah, that's right. So the reason I think what's happening, and we've done some more detailed studies on this in the past, is that when you remove the lithosphere, you take some of the lower crust with it. And so these estimates of shortening that I showed, those are over the last 35 million years. And I think they really don't represent the whole history, because we can show in some places that there really isn't any lower crust based on velocities. You get what look like quartz-rich felsic granite type compositions almost all the way to the base of the crust. Even in the altoplano, you do. So I think this has been a subduction zone for a long time. I suspect that even the altoplano has gone through some lithospheric removal. It's just been older. And then you've shoved in from the east more continental lithosphere as you've shortened it. You know, the shortening is the upper crust. And you got to figure out what to do with the lower crust and the lithosphere. And if you do those calculations where you just assume, you know, I have this much crust and this much lithosphere, there's no room for all that mantle lithosphere from the continent. So you had to have gotten rid of it just based on back of the envelope calculations. Even if you make it thin, if you have 300 or 400 kilometers of upper crustal shortening. So what does the lower crust do? Well, does it thicken in pure shear or some other way? But I think you have to have gotten rid of some of that as well. So it's perhaps a little bit misleading to show that and not explain it as probably I should have. But people are always trying to look at that. And indeed, you do have some of the thickest crust where the most shortening is. But I suspect you've lost a lot of the lower crust even. And yeah. 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 Yeah, I think you have to be losing it. And I should have made that point that, you know, when I got to that slide where now I think we have to be careful because, you know, this slab is swept through. And when the slab is there, depending on the depth, it's going to preserve whatever mantle lithosphere is there. And then when it sweeps away, perhaps, you know, then it's ripe for being removed. But even before that slab swept through, I suspect you had some removal. And in the Puna, it's a little bit harder to see the lower crust because you've got all this volcanic stuff in the mid-crust. But the moho there is clearly more gradational and more of this mesh zone than it is in the altoplano. That's right. Yeah. But it's gone. Yeah, I think with lithospheric removal, I have a slide that I took out this morning because I knew the talk was too long. But I think there are two very distinct ways you can remove lithosphere. One is in the arc, what you're talking about, where you differentiate, you're left with this high density material. And that kind of process has been shown nicely, I think, in the Sierras by various people. And then the other way is in the back arc where you shorten things and you shove crustal material deep, and eventually it is going to transform and become more dense and fall off. So you've got both of these processes that are driven by different things, one by the volcanic process differentiation, one by the shortening. And of course, they seem to probably merge together. But in most places, there's a few places that we see some high velocity material under the arc. And in fact, I have a PhD student now working on the arc. We see a lot in the lower crust in the arcs. We see this layering, high, low velocity kind of thing. And it's hard to pick the moho even. And I think that's probably showing us some of that. And then a little ways later, it seems like it's all gone. But that's a signature that shows up all the way from Ecuador to Chile. So I'm hoping he can find a way to map out that rather complicated process. I don't know if that answers your question, but no, it's a classical. Yeah. Yeah, yeah. 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 Yeah, I should have put in, I've got a nice slide of the receipt. I've got a student, as I said, he's taken receiver functions from all of these stations in the Andes. And we're trying to systematically look at and quantify how gradational the moho is and what the lower crust looks like. And in the back arc, much of the lower crust is low velocity. In the arc, it does vary, but in a lot of places, it seems to be gone. And of course, it's a little bit tricky with the melt and all that in terms of interpreting the velocities. But yeah, it's a good question. I think it has a lot of potential. At least I'm hoping. I haven't put my PhD student on a wrong track here. Wait another year and I'll tell you. But it's looking quite interesting. Yeah. Oh yeah, yeah, yeah. Yeah. There's some, I don't think so. There's some, at least not that I'm aware of, there's some local thermal models for each of them. But yeah, we're talking roughly 16 million years, maybe a little less than that, depending on where you think the slab was. But I think the ages of the volcanic rocks are pretty well determined. Now, of course, you're probably missing things, but yeah. So I don't know. Oh, I see. Mm-hmm. 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 Yeah. Yeah, I mean, it could be. We just noticed that there was a change, and there had been so much talk of the flat slab migrating through here, and that all of this was related to, that flat slab resubducting or whatever it does to become non-flat. But yeah. Well, you have to make a lot of assumptions, right, on terms of how seismic velocity relates to melt, and then you have to have composition, which we sort of think dacite, andesite kind of composition. Minimum, it's hard to say. I mean, between 5 and 10%. We were trying to be pretty generous because that's not our field, and there seemed to be so much debate about it. And how good are those experiments and that work that we're basing it on? So it could be less than that, but we thought it couldn't be more than that. And we were trying to be pretty conservative in these areas in our calculations. But yeah, it's a bit of a ballpark, but it's got to be in there somewhere. And to me, that 20% was like, are you sure that can't be right? That's a lot, I thought, coming from my background. But over such a big area, and again, it's not pure melt, but on average, so locally it could be a lot more, right? Because we're just measuring it over a fairly big area, and that integrates it. So there may be structure within that huge magma body that we can't see. Right. That's right. Yep. Yeah, that I don't know. The earthquakes tend to go a little further than that transition, at least, well, in both Peru and Argentina. So that's something we've wondered about. Like, it seems like such a dramatic end of that signature. So I can't really answer that, but I think that is one of the questions, is how, what's happening. And one of the reasons that Laura and I think, are excited about this is exactly that. The pressure is constant, right? And so now what's the temperature? In Argentina, as I mentioned, with the deep crustal earthquakes and different things, it almost seems like it's pretty cold. And there's thermal models of it with the age and all. But up in Peru, it seems like maybe it's a lot warmer, but I don't know. That's something we're trying to figure out, how to get a handle on that. You can only do so much with the age of the incoming plate, but then you've got this complication that you've had these ridges, which I would think by now are cooled by the time they're subducting. So I think there's a lot of room to do some more detailed thermal modeling based on new information. In terms of temperature, or in terms? I guess I haven't thought about it too much that way. I've certainly thought about these things underneath, the slab. And I guess I would say, let's talk this afternoon. But what would the flow field be changing along strike? We base a lot on this idea that these flat slabs form where the ridges are, and then whatever that plate does, they migrate, and the slabs are just going up and down all over the place. And they may, but I feel like maybe we're taking that too much at face value and need to be a little bit careful and keep an open mind. Clearly, slabs are flat, right? We see them now all over the world. Not all over the world, but all over the world. But one of the things I didn't point out is that the flat slabs, when they start to resubduct, but then much further inland, we still see the effects in terms of basement chord uplifts. So you can't assume, in the laramide or in Argentina that slab extended all the way to the last basement chord uplift, because Cordoba, which is one of the biggest basement chord uplifts in Argentina, the slab is at 200 to 250 kilometers depth. But again, I don't know what the flow field is, I guess. So maybe it'd be a good chance to talk to some modelers if there's some reason the flow fields would vary along strike. Yeah, right. Yeah, so I'm not a geodynamicist, but what I understand, at least from this paper that I showed, the plot age versus entrainment, that they make the point that even a 100-kilometer thick asthenospheric layer that's buoyant can still subduct if you've got a plate age that's older than about 30 million years and fast enough velocity. And I don't know who's right about that. I've seen a series of papers in Cascadia. I'm not sure I know the one you're talking about, but some of the stuff out of Richard Allen's group, they've suggested that. The reason we got going on the hotspot idea is that we were seeing low velocity anomalies. And although all the asthenosphere is kind of low, to me, it wouldn't just stand out as a really, lower than, obviously there's lows and there's lows in the asthenosphere. And so we got to thinking, well, maybe how do we explain that the asthenosphere where the ridges are going down seems to be a little bit lower than some other places. And you could throw out the idea of a hotspot and just say all asthenosphere can get entrained. And if it gets entrained, then there's a gap in the slab. Maybe it would flow through. I'm not sure we can completely answer that. But it does seem like at least some of the modeling suggests even a buoyant asthenosphere can get entrained. But I don't know. Maybe you know more about that than I do. So, but it's an interesting question, something we've been talking about in our group a fair bit as to how do you image? You image all these things, but as you guys all know, there's a big jump to interpretation, right? And it's usually non-unique. So we try to be pretty conservative, but if you buy this whole idea that we're seeing things flow through, maybe it's just mantle material at 300 kilometers depth that's just going laterally. But we thought we were seeing these lows coming down below the slab. So I still think that's a viable option. But again, where that material is coming from is always tricky. I wish seismic tomography, there was something that could image flow fields, right? And I'm not sure. We try to use anisotropy as a proxy, but it's probably not a great proxy in most cases because we don't have a depth constraint on it. It integrates a lot. So we're kind of stuck unless somebody comes up with a good way to measure flow fields.
The rest of the day. She'll also be here tomorrow, so if you didn't make it onto her schedule,